Hi, my name is Alexandre Augusto Giron. I am a PhD student at Federal University of Santa Catarina in Brazil, and I am also affiliated with the Federal University of Technology, Parana, in Brazil. I am interested in the study of the adoption of post-quantum cryptography in network protocols, and I am supervised by Professor Ricardo Custódio. The title of my presentation is Encouraging the Adoption of Post-Quantum Hybrid Key Exchange in Network Security. The outline of the presentation is as follows. First, I will start with the research problem, followed by the outline of the objectives, the state of the art, and the methodology. And in the end, I will conclude with the expected outcome and the stage of this research. The context of this research is in the key establishment methods, or key exchange. They are the first requirement to start a secure communication with symmetric cryptography, because they can be used as a solution to distribute the symmetric keys to the parties. Key exchange is present in the most widely used protocols, for example, Internet Key Exchange, Transport Layer Security, and Secure Shell, and they are often built with public key cryptography. However, there is a security threat imposed by quantum computing on cryptography, especially on traditional public key schemes of cryptography. They are vulnerable to quantum computers or quantum algorithms. Researchers started to develop and study the so-called post-quantum cryptography, where the schemes are built using other classes of mathematical problems in which there is no known efficient solution to these problems, both by quantum computers and also by classical computers. To use or to replace the traditional schemes with post-quantum cryptography, there is a set of challenges in terms of this transition process from pre-quantum cryptosystems to post-quantum cryptosystems. Examples include compatibility issues, performance issues when deployed in practice or network protocols, the interoperability between the parties or implementations, standardization process or regulations that they may force the use of one crypto system in terms of or another, and so on. But the most argument or challenge for the transition is in the confidence in the security of the PQC schemes, which are because they did not receive the same attention or research or scrutiny compared to the crypto systems that are in use today. In this context, there is a transition vision. Here is a simplified vision of this transition process where a post-quantum hybrid period takes place. So in the left of the figure, there is the known and already in use pre-quantum cryptosystems or traditional cryptosystems, such as Diffie-Hellman, RSA cryptosystem. And there is a period where the pre-quantum cryptosystems will be used or proposed to be used in combined with post-quantum cryptography together. So they are called the post-quantum hybrid or quantum safe hybrid cryptography. So they combine both pre-quantum cryptosystem with post-quantum cryptosystems. Note that in the figure that there is a quantum computer mark, which means that it's a mark in the time when the quantum computer will be publicly available or publicly or accessible to organizations and agencies and so on. And there is a period where, however, the users can be protected or expect a protection early or before this mark of this quantum computer mark. So in the middle of the figure, there is a hybrid period where users of classical computers can expect to be protected against both quantum computers and classical attackers as well. Note that in the figure it may be a small period, but it's not clear how small it is, or maybe this period may last for decades and so on, due to the difficulties in adoption or in replacement of implementations and crypto systems, and in the confidence of the post-quantum cryptography as well. So this is a period that may last for a long time, until the confidence in the post-quantum crypto systems are well established, and then in the future, in the long-term future, it is expected to that the post-quantum cryptography will replace the old or the other crypto systems. In this context, the hybrids can ease this transition. It is expected that the hybrids can ease this transition process because they use two algorithms combined, which means that at least one, in this scenario, at least one post-quantum crypto system, post-quantum algorithm is used combined with a traditional one, where the security of this construction is held as long as one of the algorithms remains secure. However, there are also challenges for this hybrid PQC design as well, which includes, for instance, the need to convey more cryptographic data compared to the original constructions. For instance, if using two algorithms, they may require two public keys or two ciphertexts and so on. This means an increase of cryptographic data being transmitted between the parties. The core of the hybrid PQC design is on the cryptographic combiner, because he is responsible to keep the security of the scheme of this construction. In addition, there is another challenges, such as the key derivation method that is often required by network protocols, and negotiation of parameters, algorithms, and also performance issues, and so on. So the main objective of this PhD research is to devise improvements and evaluate post-quantum hybrid key exchange to encourage its adoption in practice. The first specific objective is to provide a systematic mapping study of the state-of-the-art hybrid key exchange, followed by addressing these challenges of the hybrid design with improvements and evaluation and experiments using popular network protocols such as the transport layer security. The last specific objective, is to provide a security analysis for each of the modifications and proposals using this hybrid design, in order to prove or to guarantee its security. To do that, tools such as Tamarin Prover or other methods to using provable security is an objective of this study. So a summary of the state-of-the-art includes the hybrid key exchange design is regarding the selection of the key exchange algorithms, called by key exchange ingredients, composing the hybrid design. But there are some specific approaches for conveying cryptographic data, combining cryptographic data, and also the requirement often using in protocols for the key derivation, which generates the symmetric keys for the parties. So in the literature, there is some approaches. For instance, in the left, for conveying cryptographic data between the parties, the most used in the literature, or the most cited in the literature, is the concatenation approach, where, for instance, if two algorithms are used in the hybrid setting, two public keys or two ciphertexts are concatenated together and sent to the other party. A different approach to conveying cryptographic data is the hash and URL approach. However, this approach is more like a side channel exchange, since it delegates the problem to another protocol. So only the hash value and the location where the public key or the certificate can be downloaded is sent to the other party, so it delegates the problem to another protocol. The last approach for conveying is called here by packing, which means that compression techniques or packing elements to one domain to another domain in order to build a structure or in order to pack or use or transfer data more efficiently between the parties. So these three approaches are basically the mechanisms that are found in the literature to conveying cryptographic data, and in the right there is the approaches for combining cryptographic data. So projects like the Open Quantum Safe project implemented the first approach, which is a concatenation of shared secrets. So if a Diffie-Hellman is used combined with a PQC key encapsulation mechanism, for instance, both of the output of these algorithms are concatenated together. This approach is simpler to implement, but it requires a key derivation in order to derive the symmetric keys from these shared secrets. So it's simpler to implement, but requires a key derivation method, and which can be found when deploying these approaches in network protocols. There are some specific approaches to combine cryptographic data. For instance, using the exclusive OR function to build a construction for combining, and also using pseudo-random functions to build this combination. Lastly, literature shows that most approaches proposed use already defined key derivation method to derive the keys. So the hybrid setting uses a derivation already used for instance, in network protocols such as TLS or SSH. Examples include the HKDF and other hash-based solutions. The methodology of this PhD includes a set of activities, 7 activities here. The first ones are related to study, to literature review of the network protocols, and a systematic mapping study, which is an objective of this PhD. The other activities, for example, A4 and A5, include the development and design and development of the proposals. For instance, of A4, I want to explore and develop and evaluate different cryptographic combiners. And in A5, it is planned to design and compare different conveying mechanisms in the hybrid setting. The activity A6 is designed to establish metrics in regarding the evaluations, including both simulated network environments and also realistic network environments as well. The last activity is when proposing modifications, when proposing and developing new proposing new modifications, they will require a security analysis. So it is a planned activity to guarantee the security of the proposals that are made in this work. And also the last goal, or the ultimate goal of this work, is to defend the thesis, which is expected to be performed in the first semester of 2023. So to conclude this presentation, the expected contribution of this work is to support the popularization and transition to post-quantum cryptography, giving improvements and experiments and proposals using hybrid post-quantum cryptography in order to encourage its adoption in practice, and also to contribute to the evolution of widely used network protocols such as an analysis of such protocols such as TLS 1.3. The stage of this research is relatively early. It is prior to the qualifying stage of the PhD. I consider that activities A1 and A2 are done, are already performed, and A3 and A4 are ongoing work. It is planned also to submit a systematization of knowledge paper regarding activity A1 of the systematic mapping study. That being said, I thank you for your attention, and I thank you for this opportunity to present my PhD work. I'm looking forward for comments and for suggestions as well, and also to discuss or whatever subject related to to the hybrid post-quantum cryptography. Feel free to contact me, and the last slides are for the references. Thank you.